What if I told you there are objects in our universe so powerful that their magnetic fields could erase your credit card from halfway across the solar system? So rare that in our entire galaxy of 400 billion stars, fewer than 30 have ever been found. So violent that when they crack, they release more energy in 1/10 of a second than our sun produces in 100,000 years. Imagine a ball of matter the size of Manhattan spinning hundreds of times per second with a magnetic field a quadrillion times stronger than Earth's. A single teaspoon of its material weighs as much as Mount Everest. When it quakes, it tears apart the fabric of space-time itself. These objects exist. They defy everything we thought we knew about the limits of physics. They are magnetars, the rarest, most extreme stellar corpses in the cosmos. In March 1979, something extraordinary happened. Soviet cosmonauts aboard the Salyut 6 space station were conducting routine observations when suddenly their instruments went haywire. At the same moment, satellites across the solar system, American, Soviet, European, all detected the same thing, a burst of gamma rays so powerful it lit up detectors from Earth to Venus. In that fraction of a second, recalls astrophysicist Duncan Lorimer, more energy reached Earth than from any cosmic event in recorded history except for supernovae. The source? A dying star 30,000 light-years away in the constellation Dorado. Scientists called it SGR 0526-66. The SGR stood for Soft Gamma Repeater because, unlike anything they'd seen before, this object kept flaring up again and again, releasing titanic bursts of radiation. What they had discovered was a neutron star, but not just any neutron star. This was something far stranger. When massive stars die, they collapse. If they're big enough, they become black holes. But if they're right at the edge, between 10 and 25 solar masses, they become neutron stars, spheres of unimaginable density where protons and electrons are crushed together into pure neutrons. Think of it this way. If you could compress Mount Everest into a teaspoon, you'd have the density of a neutron star. The entire mass of our sun compressed into a sphere the size of Manhattan. A single cubic centimeter weighs as much as 400 million elephants. But SGR 0526-66 was different. It had a magnetic field unlike anything in the known universe. To understand just how powerful, consider this. Earth's magnetic field is about half a Gauss. A refrigerator magnet is 100 Gauss. The strongest magnetic field ever created in a laboratory is 100,000 Gauss, and it can only be sustained for a few milliseconds before the equipment tears itself apart. The magnetic field around SGR 0526-66 measured 100 trillion Gauss, 100 trillion times stronger than Earth's field, a quadrillion times more powerful than any magnet you've ever encountered. Scientists needed a new name for such an object. In 1998, astrophysicist Robert Duncan coined the term magnetar. But discovering magnetars raised more questions than it answered. How could such extreme magnetic fields exist? What powered their violent outbursts? And most troubling of all, if these objects were real, where were they? Why were they so impossibly rare? But the evidence forces us to confront an uncomfortable possibility that the universe's most extreme physics occurs not in black holes or during the Big Bang, but in these stellar corpses scattered like rare jewels across the darkness. The evidence for magnetars began accumulating slowly, piece by extraordinary piece. First, the rotation. When neutron stars form, they spin fast. Most neutron stars spin hundreds of times per second, their incredible angular momentum preserved from their parent star's collapse. But magnetars are different. They spin much slower, typically once every 2 to 12 seconds. Why? The answer lies in their monstrous magnetic fields. As these fields interact with surrounding space, they act like cosmic brake pads, slowing the magnetar down over millennia. This discovery provided the first concrete signature. Find a slowly rotating neutron star with the right properties, and you might have found a magnetar. By 2005, astronomers had confirmed fewer than a dozen magnetars in our entire galaxy. These weren't just rare, they were needle in a cosmic haystack rare. For comparison, there are estimated to be 100 million neutron stars in the Milky Way. Magnetars comprise perhaps 1 in every million. Second, the outbursts. Magnetars don't die quietly. They experience what scientists call star quakes, catastrophic cracking events in their ultra-dense crusts. Picture the surface of a magnetar. It's solid, crystalline, a lattice of iron nuclei 1 billion times denser than steel. But underneath, the star's intense magnetic field is constantly shifting, building up stress. When that stress exceeds the breaking point, the crust fractures. When this happens, the energy release is incomprehensible. On December 27, 2004, magnetar SGR 1806-20, located 50,000 light-years away, experienced a mega flare. For 1/10 of a second, it became more luminous than anything in our galaxy except the Sun. The blast of gamma rays and X-rays disrupted Earth's ionosphere from halfway across the galaxy. Dr. Brian Gansler of the University of Sydney put it simply, if this happened at a distance of 10 light-years, it would have caused a mass extinction on Earth. The energy released in that fraction of a second, equivalent to what the Sun produces in 100,000 years. Third, the magnetic field structure itself. Using X-ray observations from NASA's Chandra telescope and ESA's XM Newton, astronomers mapped the magnetic field topology around these objects. What they found defied classical physics. The fields aren't simple dipoles like Earth's relatively orderly north-south configuration. They're twisted, braided, knotted, complex three-dimensional structures that shouldn't be stable according to conventional magnetohydrodynamics. Yet they persist for thousands of years. And here's where it gets truly strange. The magnetic field energy exceeds the rotational energy. In normal pulsars, the rotation powers everything, but in magnetars, the magnetic field is the dominant energy source. The field itself is slowly decaying, powering the outbursts, the X-ray emission, everything. As observations accumulated, the implications grew more profound and more disturbing to conventional physics. In 2007, astronomers discovered something unexpected. Some magnetars were associated with supernova remnants that were far too small, suggesting these stars died only a few thousand years ago. But neutron stars typically cool down and become invisible within a few million years. These magnetars were cosmically young, still blazing with residual heat. This led to a startling realization. Magnetars might not be a permanent state. They might be a phase, a violent adolescence that neutron stars pass through before settling into quieter old age. Every magnetar we see might be a recently formed neutron star, still crackling with the energy of its violent birth. Then came the fast radio bursts. In 2020, astronomers detected something that changed everything. A fast radio burst, one of the most mysterious phenomena in astronomy, bright radio flashes from across the universe lasting mere milliseconds, was detected coming from inside our own galaxy. And the source? Magnetar SGR 1935 plus 2154. For years, scientists had debated what caused these enigmatic bursts detected from billions of light-years away. Colliding neutron stars? Evaporating black holes? Alien civilizations? Now they had an answer. At least some fast radio bursts come from magnetars. Dr. Shami Chatterjee of Cornell University explains, this was the missing link. For the first time, we caught a fast radio burst in the act and identified its source definitively. But how do magnetars produce these bursts? The leading theory involves something called magnetic reconnection, when twisted field lines suddenly snap and reconnect, releasing enormous energy in the process. The same phenomenon powers solar flares, but amplified 1 trillion-fold. Yet this raises a deeper question. If magnetars are responsible for at least some fast radio bursts, and we detect thousands of these bursts from across the cosmos every year, then the universe must be filled with magnetars, far more than we've found in our own galaxy. Which means either we're drastically underestimating how common these objects are, or the conditions that create magnetars were more prevalent in the early universe. Either possibility challenges our models of stellar evolution. Then there's the quantum mystery. At the intensities present on a magnetar's surface, quantum mechanics breaks down. The vacuum itself, the empty space we think of as containing nothing, becomes polarized. Virtual particles pop into existence and disappear. Light doesn't travel in straight lines anymore. The magnetic field is so strong it bends photon paths. Dr. Nanda Rea, leading magnetar researcher at the Institute of Space Sciences in Barcelona, notes, "These objects are natural laboratories for extreme physics. The conditions near a magnetar's surface simply don't exist anywhere else in the universe. They're testing our physical theories at their absolute limits." In regions where the magnetic field exceeds 100 trillion Gauss, atoms elongate into thin cigar shapes. Electrons can only move along magnetic field lines, creating one-dimensional quantum wires. The very structure of matter changes. The evidence extends beyond astrophysics into the realm of fundamental physics itself. These stellar remnants are rewriting the laws of nature. So how does a neutron star become a magnetar? The leading theory centers on the moment of formation, those chaotic few seconds when a massive star's core collapses. During core collapse, the progenitor star's magnetic field is compressed along with its matter. As the field lines are squeezed into a smaller and smaller volume, the magnetic field strength increases exponentially, a process called flux conservation. It's like taking the balloon's worth of magnetic field and compressing it into a marble. But that alone isn't enough to create a magnetar. You need an additional ingredient: rapid rotation. The theory proposed by Duncan and Thomson in 1992, now called the dynamo model, suggests that if the nascent neutron star spins fast enough immediately after formation, convective motions in its still liquid interior can amplify the magnetic field through a process called the magneto-hydrodynamic dynamo. Think of it as a cosmic generator spinning at unimaginable speeds. Within the first 10 seconds of a neutron star's life, while it's still cooling from temperatures of 100 billion degrees, this dynamo can boost the magnetic field strength by factors of thousands or even millions. But here's the critical factor. This process requires very specific conditions. The progenitor star needs to be rotating rapidly, the collapse needs to happen just right, and the neutron star needs to be born with a mass right at the edge of stability, heavy enough to have the density required, but not so heavy it collapses into a black hole. This explains their rarity. Most massive stars don't meet these criteria. They're either rotating too slowly or too quickly. They're either too heavy or not heavy enough. The window for magnetar formation is extraordinarily narrow. Dr. Krissa Kuvalatiu, who made pioneering magnetar observations, puts it succinctly: magnetars are cosmic accidents. They require everything to go wrong or right in just the perfect way. But there are competing theories. Some astrophysicists propose that magnetars might form from the merger of two white dwarfs, stellar remnants that spiral together and collapse into a super-dense neutron star. Others suggest that very massive stars with initial masses above 40 solar masses might preferentially form magnetars due to their internal structure. What's clear is that we're still piecing together the puzzle. Institutions like the European Southern Observatory, the Chandra X-ray Chanta, and radio telescope arrays worldwide are continuously monitoring known magnetars and searching for new ones. This forces us to reconsider fundamental assumptions about stellar death, magnetic field generation, and the diversity of neutron star populations. Then there's the implications. Ancient cosm, magnetic force, elusive evidence. As magnetar cosm. As we look deeper into magnetars, the implications become almost unsettling. Consider this. The magnetic field of a magnetar is so powerful that if one existed 100,000 kilometers from Earth, halfway to the moon, it would strip the iron from your blood. Your body's biomagnetic field, which normally keeps you functioning, would be utterly overwhelmed. You wouldn't just die, your molecular structure would begin to warp. But it goes further. Recent theoretical work suggests that the interior of a magnetar might contain exotic forms of matter that don't exist anywhere else in the universe. Hyperons, strange baryons containing strange quarks. Possibly even quark matter itself, where the boundary between individual protons and neutrons breaks down entirely. We cannot recreate these conditions in any laboratory. We cannot simulate these pressures or densities with any current technology. The only experiments nature runs at these extremes happen inside magnetars. Dr. Todd Strommeyer of NASA's Goddard Space Flight Center raises a provocative question. What if magnetars aren't just rare? What if they're temporary? What if every neutron star passes through a magnetar phase, and we only see a fraction of them because the phase is so brief? If true, that would mean magnetars aren't cosmic accidents, but an inevitable stage in neutron star evolution. Every pulsar we observe might once have been a magnetar, blazing with impossible magnetic power. Then there's the question of magnetar planets. Could a planet orbit a magnetar? Theoretically, yes, but it would be sterilized by radiation, its surface constantly bombarded by high-energy particles. Any atmosphere would be stripped away in years. The very rock might become charged by the magnetic field, creating planetary-scale electrical currents. Yet some scientists speculate about exotic possibilities. Could organic chemistry occur under such extreme magnetic fields? Could there be forms of matter or energy we haven't conceived of, unique to magnetar environments? The most profound implications emerge when we consider magnetars in the context of fast radio bursts. If these objects are sending out powerful radio signals that propagate across billions of light years, then every galaxy with active star formation should have magnetars, millions or billions of them across the observable universe. We are surrounded by these extreme remnants of stellar death, most too distant or too faint to detect directly. They are monuments to violent creation, markers of a universe's capacity for extremes. And in their magnetic fury, they raise the ultimate question: what else exists out there that we haven't yet imagined? What other exotic states of matter, what other extreme phenomena lie waiting to be discovered? We began by asking what the rarest objects in the universe might be. We found our answer in magnetars, stellar corpses so extreme they rewrite the laws of physics, so powerful they can disrupt planets from across a galaxy, so rare that we found only a handful in our cosmic neighborhood. These objects represent the universe at its most violent and creative. Born in the collapse of massive stars, sustained by magnetic fields that challenge our understanding of nature, they bridge the gap between matter and energy, between order and chaos. We know they exist. We know they're rare, perhaps one for every million neutron stars. We know their magnetic fields are the strongest in the universe, that their star quakes release more energy than our sun will produce in millennia, that they may be responsible for mysterious radio bursts from across the cosmos. But we don't know how common they truly are. We don't know what exotic matter exists in their cores. We don't fully understand how their magnetic fields persist for thousands of years, or why some neutron stars become magnetars while others remain ordinary pulsars. The study of magnetars is a testament to human curiosity, our drive to understand even the most extreme, the most distant, the most incomprehensible phenomena. These objects will never threaten Earth. We will never visit one. But in studying them, we push the boundaries of knowledge itself. The universe is vast. It contains wonders beyond imagination, objects so rare, so extreme, that finding them feels like discovering hidden jewels in the cosmic dark. The mysteries are endless. The journey continues. And somewhere out there, 30,000 light-years away, a magnetar spins silently through the void, its magnetic field powerful enough to reshape reality itself, waiting for the next starquake to remind us that the universe is far stranger than we dare to dream.